Hello everyone, this is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics, fully online. And this week we're going to be doing Chapter 13 on the repeated measures and two-factor analysis of variance. So there's a lot going on in this chapter, so we're going to take it step by step. And you need to practice the problems, ideally uh, in the Cengage product in the MindTap, where you have the step-by-step problem demonstrations, problem tutorials. You should be doing that, and also doing that on your own. Doing the problem from scratch on your own. So that will help you with, a few different calculations that we're going to see in this chapter. So in this chapter, we're going to be talking about why you would want to run a repeated measures ANOVA study. We'll be computing the repeated measures ANOVA and looking at the difference between the single factor ANOVA that we did last chapter and the repeated measure study. We'll be looking at effect size and performing post hoc tests within the repeated measures ANOVA. We're also going to look at the two-factor factorial design, which is basically two independent variables that can possibly interact and create a more meaningful effect called an interaction effect. And we'll be studying both those interaction effects from those two variables interacting together and the main effects, which is the effects of each variable by itself in the two-factor ANOVA. Now, you can have more than two-factor ANOVAs, but it would be a nightmare to do it by hand with anything more than two. Then we'll be talking about effect size and the computation of the factorial ANOVA and results in terms of APA style. So we did talk about the analysis of variance last time, and the analysis of variance looks at three or more groups. Now, when you have a factorial ANOVA, which means you have two independent variables, you can have basically two levels for each one, right? But we're talking about in total, you have to have three or more groups, which you will have basically with any single factor ANOVA and any factorial ANOVA. Now, previously we talked about a setup with ANOVA where we had one independent variable and obviously one dependent variable. Now we're going to extend that to both the repeated measures version, where we have the same people taking part in multiple levels of that independent variable. Before, we really talked about the independent design, where you had different people in each level. Now we're going to have the same people in each level, which is the repeated measures ANOVA. And then also the not the multivariate, but the factorial ANOVA, where we have two or more independent variables and obviously one dependent variable still. And how do those two or more independent variables interact to create, a result on a dependent variable that is different than what you would have with each independent variable alone. So this sounds very complex. It's really not. It's just a different way of thinking about solving the problem. We went from one ANOVA with three or more groups. Now we're stepping it up to do either repeated measures version of that or two independent variables in this situation with the factorial design. So the independent measures ANOVA, which we did last week, something that's called the one-way ANOVA. You had different samples of people in each of the treatments. So you had three or more groups and different people, different samples in each of those three or more groups. Those samples were not the same people. Now with the repeated measures, we're going to have the same people in three or more groups. Now the most common setting where you see repeated measures used is if you have like the same people measured over a period of time. So remember I talked about the repeated measures t-test where you had pre-test and post-test? Well, what if you had pre-test, post-test, and then 6 months later? So now you have three different time periods, and if you're using the same people in each of those three different time periods, you're going to have repeated measures ANOVA. So all I've done is extended the repeated measures t-test by adding another time period to make a third group or a fourth group, or how many groups you need. And this is very common in longitudinal research where you're trying to study the same people over a period of time and you want to see what changes there are. That could be with medication, that could be with just a normal process of people maturing. It could be performance-wise, like you're measuring their verbal or mathematical ability over time. So there's many different experiments or research studies where you see this kind of problem. We treat these three or more groups, since they're the same people, we treat them basically as one group measured over time. So there's no individual differences like you saw in the previous independent group design, where you said, well, people could be different in each group, and it could be that the fact that people are different, there's individual differences because there's different people, and that could be driving the result. That was a problem with the independent groups design, the one-way ANOVA. Now, if you're using the same people in each of the conditions, then individual differences no longer matter. So we can actually get rid of them statistically, and that's what we're going to be doing for the repeated measures ANOVA. So as I mentioned, you have three or more groups, and you're using the same people in those three or more conditions. Now, ideally, it's different time periods where you're testing them at time 1, time 2, and time 3. However, you could have it where you're testing, you're giving them different treatments. So, I mean, technically, you could have a repeated measures where you get placebo, you get 5 milligrams of the drug, and then you get 10 milligrams of the drug. That's 3 treatments, and you could participate in each one of those. I would not run that kind of design, but you could run that design. And the reason I wouldn't run that design is because if you're getting one version, either the placebo or the drug, or a certain dosage of the drug, that may interfere with what happens later on. So with that kind of design, you need to have counterbalancing, which means that if you start with the placebo, then someone else has to start with the drug. And if there's 3 groups, then a third person has to start with the a different dosage of the drug. And so it has to be balanced out so that everybody gets different orders, so that the order in which you receive the treatment doesn't affect the outcome. So when you have a situation like that, you could run it as repeated measures ANOVA with the same people getting each of the 3 treatments in a different order, counterbalancing the order. I would not do that. I don't think that's a good way to run a study. I think if you have 3 treatments, you should have 3 different groups. Run it as between groups. Run it as independent groups design. Do not run it as repeated measures. But if you're doing if you're testing the same people at multiple time periods, that makes sense to run that as repeated measures. And that's what this design is mainly used for. The null hypothesis is the same as it was with the independent groups ANOVA that we talked about last time. It's that all the means are the same of all the groups. So if this is different time periods, then there's no change in different time periods. Whatever we're measuring is going to be the same. Let's say I gave you an intervention to decrease your levels of aggression, and I wanted to monitor every 3 months. I took a measure of your aggression levels, and I want to see, does my intervention work over a period of a year? So I'm taking basically 4 measures at 3 months, 6 months, 9 months, and 12 months. That would be repeated measures ANOVA. However, my null hypothesis is still going to be the same. I'm going to say there's no difference. There's no difference in aggression between the 4 time periods that I'm looking at. The alternative is that there is some kind of difference. That means they're not all going to be the same. At least one treatment is going to be different from another, at least one. I don't know where that's going to be. I don't need to know where it's going to be. I can then follow up and do post hoc tests if it's significant. But the alternative is that there is some difference. So the F ratio is the same as it was in the univariate, in the between groups or independent groups design. The numerator of the F ratio is the treatment effect. So is there a difference caused by the treatment, over those multiple sessions or between the multiple groups? In the case of repeated measures and you're using the same people in 3 or more time periods, then, is there a treatment effect over those 3 or more time periods? There's also going to be some random chance differences, although those are going to be reduced. Now, the reason I'm saying there's going to be random chance differences is you're taking a sample, and the sample is from the population. You would hope that that sample is representative of the population, but you can't guarantee that. Obviously, the larger the sample, the more representative it will be. But you can never be 100% sure that your sample represents perfectly the population. So there's going to be those kind of what's called sampling error. The difference between the sample mean and the population parameter, population mean, is sampling error. You're always going to have that. That's what I call chance. That's not individual differences because you're using the same people in each of the 4 conditions or 3 or more conditions. So there's no more individual differences because you're using the same people. So any variation over time is going to be due to either the treatment or due to chance factors. The denominator represents what would occur if the null hypothesis is true. So if the null hypothesis was true and there was no treatment effect, there would be some difference. The difference probably wouldn't be great between the multiple treatments, but there'd be some difference, and that would be chance differences. So basically the numerator is the treatment, and there's always going to be some chance associated with that. And the denominator is just chance. And so if the numerator is much bigger than the denominator, then we know that it's not just chance that's causing the difference between the treatments. It's really due to the treatment itself. The independent variable that you're manipulating, the treatment that you're giving, is working in some way. So the bigger the F ratio, the bigger the effect of the treatment. So the F ratio is based on variances. So once you get the sum of squares, which are the sum of the squared differences, you then convert them into what is called mean squares by dividing by the degrees of freedom. And you get the F ratio. The F ratio is basically a ratio of 2 variances. The treatment variance is on top, and the variance is due to chance is on the bottom. That's basically what I just said before. Now you do have individual differences when you're doing an independent group's design. So if you have different people in each of your treatment conditions, those groups could be different because of different people, in those groups reacting different. So you always have to contend with the fact that you could have individual differences due to the fact that you have different people in each group. That's always a concern with the independent groups design or between groups design that we did last time. When you have different people in each condition, you're going to have individual differences that are going to increase the amount of error that you have, increase the amount of chance variation, because individual differences is part of chance variation, right? It's not only the people that you select, it's the fact that you're selecting different groups of people and they may not all be alike. Even if they come from the same population, people are different with regard to a lot of different things, and that can affect their response to the treatment. So when you're using different people in an independent group's design, you always have to contend with the fact that they're different people, and that's going to introduce more chance or more error to your problem, to your experiment. And you just hope that the treatment is so strong that the treatment overwhelms, is much greater than any kind of chance variation due to individual differences and due to sampling error. And that's why the denominator for the F ratio, when you're using different groups of people, what's called the independent groups design or the between subjects design that we talked about last time. Uh, when you're doing that, you're going to have a bigger denominator because the denominator is going to include the individual differences due to different samples. The repeated measures design is better than that in some ways. It reduces the error because it removes those individual differences. So as a result, the denominator gets smaller. And when the denominator gets smaller, it becomes easier to reject the null hypothesis. And that's why there's an advantage statistically in using repeated measures ANOVA versus using independent groups ANOVA. Because the denominator will be smaller with the repeated measures ANOVA because you're subtracting out the variation caused by individual differences. So it's more powerful, has more statistical power. That doesn't mean it's better because there's pitfalls with the repeated measure design. The biggest pitfall is the order in which you receive the treatment. Or stuff happens to people over time. I mean, I've run these designs many times in studies. Unfortunately, I've had the I've had the pleasure of running these kinds of repeated measures ANOVAs, and it's a problem because you might want to test people at 3 or 4 different time periods, but guess what? They don't show up. You can't call them. They don't answer your calls. They don't answer your texts. They don't answer their emails. They're gone. So now what? Wouldn't it just be easier to like get different groups of people and test them all at one time and run an independent groups design where you're only testing them once versus taking the same people and running them 3 or 4 different time periods? The answer is yes. It's a hell of a it's difficult. It's a hell of a problem when you lose like half your sample, which can happen. I've seen it personally happen to me, where I did like pre-post and I tried to do like 6-month follow-up. Forget it. I could barely get pre-post. Now if I'm waiting 6 more months to follow up with these people, I'm going to lose them. So that's probably the biggest problem with the repeated measures ANOVA is if you're bringing people back multiple times to be tested, you're going to lose people. So it doesn't matter if your statistical power is higher, because if you're losing half your sample, it's going to kill your statistical power anyway. So that's the real pitfall. If you're going to do repeated measures, either A, do it close together in time if possible, or B, make sure that you have a team of people ready to reach out and follow up with people. So you bring them back, because it's so difficult to bring people back multiple times to be retested. And as I was mentioning, the biggest advantage of using the repeated measures is you remove the individual differences. So statistically, it's better. From a practical point of view, it may not be better. It really depends on what study you're running, and maybe you have better luck than I have running my studies. Or maybe you don't want to use BMCC students, because BMCC students never follow up. They don't answer their texts, their emails. Some of them do. A lot of them don't. I had my research assistants reaching out to them, and they're gone. Even if I'm going to pay them at the end of the study, they still disappear. Why? Because BMCC students are very busy, and there's a lot going on, and unfortunately, research takes a backseat to everything else. So maybe if you're using a population that you can easily contact, it might work out better. But BMCC students, it tends to be difficult to bring them back multiple times. So how do we compute this repeated measures ANOVA? So there's 2 stages to the computation. The first stage is the same thing that we did last time, the independent groups ANOVA. So you compute the sum of squares total, you compute the sum of squares between, and you compute the sum of squares within. Now the difference is, after you've done all those, which is the same thing you did last time, you need to take that sum of squares within, and you've got to subtract the individual differences. The individual differences is called the sum of squares between subjects. So once you subtract the sum of squares between subjects, which is individual differences. You subtract that from the sum of squares within, you'll get something called the sum of squares error, which is also known as residual, the leftover. That sum of squares error now becomes the denominator part, right, the mean squared error. When you take the sum of squares error and divide by the degrees of freedom of error, you're going to get the mean squared of error. That's going to be the denominator of your F ratio. And that denominator is going to be smaller than the sum of squares within, because you've subtracted the variation due to individual differences, the sum of squares between subjects. So that denominator is getting smaller, and then your F ratio is going to be bigger. So basically your F ratio now is going to be the treatment effects in the numerator. Obviously there's no individual differences there because they're the same people. And then the denominator, you're going to have to subtract the individual differences out of the denominator. And the reason you have to do that is because for the numerator, you have clear differences between the treatments, right? Between the conditions that they're in, you can see the clear differences. You don't have any individual differences that would, convolute looking at the difference between the different treatment levels. You don't have that anymore. But in your sum of squares within, you still have those individual differences. And so that has to be statistically removed. So you don't have to remove anything from the numerator, but you have to statistically subtract the individual differences from the denominator. And that makes the denominator smaller, that makes the F ratio bigger. So you have your total variance divided into between and within. The between is the treatment effect, the numerator. The within is sampling error, which is chance. It's also individual differences. You then need to subtract out individual differences. That's called the between subjects variance. And then whatever is left over is called the error variance. And that becomes the denominator of your F ratio. So it's the same thing that you just did, except there's one more step. You have to calculate and subtract the sum of squares between subjects. The between subjects variance, which is the sum of squares between subjects. And you're going to get a smaller denominator called the error variance. Sum of squares of error becomes mean squared of error. So here's a review of the formulas you did last time. So you had sum of squares total, which is the sum of all the squared scores. So take each score in the whole sample across all groups. So every score in your experiment, square it, add that all together. That's going to give you the sum of x squared. Then minus g. G is the grand total. So just add up all the scores in your study across all the different treatments. So every single score gets added together and becomes g, grand total. Square that quantity, divide by the total sample size, capital N. Then your sum of squares within is going to be basically the sum of squares. Find the sum of squares in each treatment group. So once you find the sum of squares in each treatment group, add them together. And then the sum of squares between treatments, which is the numerator, is going to be the sum of the totals. So these are the totals. So the sum of scores in each group is the T, or total. So when you add up all the scores in each group, you get T. Square that total, divide by the number of individuals in each group, which is little n, and then subtract the grand total squared over the total sample size. So these are identical steps to what was just done. Now here's the new equations. You need to find the sum of squares between subjects. So you're going to add up the participants, capital P. Capital P is the sum of all the rows, right? So capital T is the sum of all the columns, which are the treatments. Capital P is the sum of the rows. So every individual gets a different row. And capital P is just the sum of that individual scores across all the treatments. So it's the row sum. Once you get those row sums, you're going to square them, divide by the number of treatments, which is k. So add up the row sum, which is capital P, square it for each individual, divide by k, minus the grand total squared over the total sample size. That's going to be the individual differences. So basically it's the difference in each participant between the treatments. That needs to be basically filtered out. That's going to be subtracted from the within groups sum of squares. So the error term, sum of squares of error, is going to equal sum of squares within minus sum of squares between subjects, I should say, I'm sorry. Sum of squares error is the sum of squares within minus the sum of squares between subjects, not the sum of squares between groups, between subjects, which is the individual differences. Now, once you have the sum of squares, you need to have the appropriate degrees of freedom. So degrees of freedom total is n minus 1. The degrees of freedom within treatments, you just add up the degrees of freedom for each treatment, or you could just do n minus k, where k is the number of groups. The degrees of freedom between treatments is k minus 1, where k is the number of groups. The degrees of freedom between subjects is the number of participants minus 1. So it's not the total data points, it's the number of participants minus 1. Whereas degrees of freedom total is the number of total data points minus 1. And it's not the number of participants, it depends on how many data points, how many scores do you have, basically. The degrees of freedom error is the degrees of freedom within, right, minus the degrees of freedom between subjects. Or you can compute this using k minus 1, where k is the number of groups, times n minus 1, where n is the number of participants. So these are just general rules that you're going to have to be familiar with when you compute the problem. And once again, I can't emphasize enough, do the problem tutorials in MindTap, where it says, show tutorial, it'll walk through everything step by step, and then it'll say like tutorial practice problems, do them. I mean, you can always ask me, you can always reach out through email or, sign up for office hours, and I can sketch out some things or go over some things with you. But you should practice first. See if you can sort of understand the basics. Do some practice problems on MindTap, and then do some problems on your own, like on paper, away from the computer. I always find it helpful to, if you just practice on the computer, to do things also like on your own without the computer sort of guiding you step by step. Can you do the problem from scratch? Now, most of the stuff is going to be on the test. I'm going to ask, I think, fairly reasonable questions. I'm not going to make it super difficult, but you need to know the process. And you should be able to follow the steps. Now, to find the mean squares, which are variance estimates, the mean squares between treatments is obviously the sum of squares between treatments divided by the degrees of freedom between treatments. The mean squared error is simply the sum of squares error, and the sum of squares error you got when you did sum of squares within minus sum of squares between subjects, which is the individual differences. That gives you the sum of squares error, divided by the degrees of freedom of the error. And then the F ratio is the mean squares between treatments divided by the mean squares of the error term. And then you're going to look up the critical value just like you looked it up last time in the F table. If you're looking at effect size, We don't have eta squared like we did before. Now we have partial eta squared because we're not looking at all the variability. We're only looking at some of the variability. We want to look at the variability that's due to the treatment compared to the variability due to the error and the between groups sum of squares variability. So in general, there's two formulas you can use. You could either use the top one, which is the sum of squares between treatments, over the sum of squares total, and then subtract the sum of squares between subjects. Now that denominator is equivalent to the second formula, where in the denominator you have sum of squares between treatments plus sum of squares error. So those are equivalent formulas. You can use whatever one you want. I think the first one is fine. The second one's fine. There's really no difference. They're equivalent, right? But this is partial eta squared because we're not considering the total variance. You see how the total variance is not in the bottom? The bottom, the denominator is something less than the total variance. So since we're considering something with less than the total variance, we have partial eta squared as your measure of effect size. Because we're not considering the total variance. We were considering the total variance in the between subjects, the independent groups ANOVA that we talked about last time. Now in the literature, you could report the F ratio as F, capital F, means you did the ANOVA. Parentheses, the first number, 3, that's the between groups degrees of freedom. That's the treatment degrees of freedom, right? Comma, the 18 is the error degrees of freedom. So it's no longer the within groups, it's just the error degrees of freedom. So here you have 3, comma, 18 being the error degrees of freedom, is this large number, 16. Obviously that's significant at 0.01. And the partial eta squared is 0.859, which is really, really strong. So this is a very, very strong result. The treatment is having a big influence. Now with the significant F value that you obtain if you're running repeated measures in ANOVA, that basically means that not all the conditions are the same. So there's some effect of your independent variable, whatever treatment you're using is working in some way. But we need to know exactly where the differences lie. And so we're going to do post hoc tests once again. The same post hoc test that we did with the independent groups design last time. And the post hoc tests include the Tukey's honestly significance difference test and the Chaffee, although I much rather use the Tukey's honestly significance difference test because it's more powerful to see if there's differences. Now, the only difference you do with the Tukey test is you're going to substitute, instead of SS within, sum of squares within, you're going to replace it with the sum of squares error. So it's going to be a smaller number, and the degrees of freedom within is going to be replaced by degrees of freedom error. And you use that degrees of freedom error to then look up the critical values to find the values in the table. Well, to find the Q value actually. So you're just substituting error instead of within in these formulas. Some of the assumptions, they're the same assumptions we had with regular ANOVA, between groups ANOVA. Independent treatment conditions must be independent. That means basically the score in condition 2 should not be influenced directly by the score in condition 1. The score in condition 3 should not be influenced by the score in condition 2. These should be independent conditions. There should be no carryover. If there's a carryover where there's some kind of influence on subsequent data collection, so if you're going to measure them at 3 points a time and what you did at time 1 is going to influence time 2 and time 3, then it's probably not a good idea to run repeated measures. You're probably better off running the between groups ANOVA that way. So you need to have independence of observations. You need to have normal, so the samples have to be coming from a normal population for each of those conditions. And one way to guarantee this is you have a sample size in each group of 30 or more. So if you have 3 groups, you want to have at least 90 people. Now, you may not have that, and then you have to make a determination. If the sample sizes are relatively equal between the groups, then you can have some non-normality and you'll be fine. You just don't want the samples to come from a distribution that is highly skewed. So as long as you don't have heavy skew in your samples, you're probably safe. Or you have like really unequal sample sizes. You know, you don't want to have like 100 people in one condition and then have like 30 in the next, especially with the repeated measures. That would be a disaster. That means you lost 70 people. You definitely wouldn't want that. So if you have near equal sample sizes, this is not usually an issue. And then the homogeneity of variance assumption. The variances have to be relatively the same. So you have that Hartley's Fmax test that the book talks about when you go back to the independent groups t-test, where you put the 2 variances and you form a ratio and you look up the ratio in the table. That's fine. You can use, there's other things called the Levene's test of equality of variances is used. There's something called sphericity, but we're not going to talk about that. That's a big mess. But there is technically an assumption called sphericity that has to be met, which has to do with the covariances. And we're not going to talk about sphericity. It's generally not a problem, but it could be. And it tends to happen with the repeated measures ANOVA. But you need to make sure the variances are relatively the same within each of the conditions. So you don't want the larger variance to be more than 4 times the smaller one. So as long as the largest variance is no more than 4 times the smallest variance, you should be pretty much okay. But if you want to run Hartley's Fmax test and look up the value in the table to do a formal hypothesis test, you could do that, or Levene's test, which I think is better, but the book doesn't talk about it. The statistical software will do this for you. Very rarely do you do any of these things by hand. Although it's good to learn simple problems by hand. If you had like a huge data set, let's say you had like thousands of people, you certainly wouldn't be doing it by hand. Let's look at the learning check here. A researcher obtains an F ratio with degrees of freedom 2 and 12 in a repeated measures ANOVA. So how many subjects participated in the study? Well, we know that the first number is the degrees of freedom between, and we know that the second number here is the degrees of freedom error. So we need to know both of these to figure this out. So the degrees of freedom error, based on the equation I gave you a few slides ago, is equal to n minus k times n minus 1. So in this case, degrees of freedom error is 12, and it's equal to n minus k. I'm sorry, wrong formula. Degrees of freedom error is equal to k minus 1 times n minus 1. That sounds better. K minus 1 times n minus 1. So here, k minus 1 is equal to 2, because we see 2 degrees of freedom, and we know that 2 degrees of freedom is k minus 1. So k is 3, and 3 minus 1 is 2. So k minus 1 here would be 2. And then n minus 1, we don't know what n is, right? We're solving for n. So this becomes 2 times n minus 1 is equal to 12. So since I have 2 and I have 12, and they're both even numbers, divide both sides by 2. So if I divide 12 by 2, I get 6. If I divide 2 times n minus 1, I get n minus 1 when I divide by 2. The 2's cancel. So I get 6 equals n minus 1. Add 1 to both sides. 7 equals n. So the answer here is 7. So I have 7 participants here in this design This goes back to the formula: degrees of freedom error is equal to k minus 1 times n minus 1. So let's just plug in and solve. And the answer, obviously, is 7. So the advantages of repeated measures. Individual differences do not influence the outcome. So there's less variability, there's less error variability, or the denominator or the F ratio is smaller because you don't have individual differences. And it could also be more cost effective because you need less people to test all the treatments. Since you're using each person in every treatment condition, you don't need as many people. So it could be cheaper because you don't have to pay as many people. So those are, so it's more powerful because the denominator is smaller in the F ratio. So you have higher statistical power. It requires less people, which is less money. So it sounds like a really good deal, except when participants disappear. So that's always a problem, right? So you have things called history effect, which is basically things that happen between the treat, the treatment conditions, right? So condition 1 and condition 2, let's say it's 6 months apart. In those 6 months, a lot of things can happen. And those things that happen to the participants could influence their response 6 months down the line. That's a big problem, right? So the biggest history incident that I could ever remember is the global pandemic, right? So I was running a study in the spring, and we were gathering subjects, and we were doing repeated measures. And just when we started doing condition 1, we were going to then do the treatment and then follow up, a few weeks later for condition 2, the pandemic happened. And basically, that was it. That was the end of all research. So I basically lost all the participants because we couldn't even get into the building. So how are you going to run a study? Uh, that is an example of the problems with the repeated measure design. I mean, chances are you're not going to have a global pandemic to screw up your study, like I had this last semester, but you're going to have other things, like the person moves. Guess what? They're not going to be in your study anymore. The person is has a kid, or has another major life event, gets divorced, or besides moving, gets fired from their job, etc. Gets sick in another way. So all of these things that can happen between treatment conditions can really blow up your study. And that's the biggest problem is, if you're running a study over a long period of time, it's going to be really difficult to keep those people motivated. Even if you pay them, it's still not enough. People don't care. You're paying them. It's like, oh, well, I have other things to do. I'm sorry. I mean, even if I don't get paid, it's fine because let's say I have another job, and that job pays me more than what you're going to pay me as a research participant. These things happen, and you can't get mad. It's no one's fault. It's just very frustrating as a researcher. So experiences in their personal life, in their professional life, in the world, different factors can really screw up a repeated measure design. And those are the real pitfalls, especially when you lose subjects. Or maybe something happens and participants will react differently later in the study than they did earlier on. So maybe they don't drop out, but they just react completely differently. So you're not getting consistent results because something changed about their mentality, their life circumstance, etc. Um, you also have practice effects. So if you give the same assessment multiple times and it's the same thing, people get better at it. So if you're trying to test people's math ability and you give them, every 3 months you give them the same math test, well, are they getting better because you're doing some kind of intervention to help them, or are they getting better because they're seeing the same test over and over again and they're getting more familiar with it? That's practice effect. So you have to be aware of those situations. That could all basically blow up your study. So I do like repeated measures design, but the huge caveat is that Even though statistically it's more powerful, it may not be worth it to you because it's a hell of a lot more work and it's a big hassle. And I can't think of another way to to examine like treatments or interventions. This is the best way to do it, but at the same time, it's incredibly frustrating because so many things can happen and they're kind of out of your control. So use it when you need to use it. Try to keep the time periods the shortest apart as possible. You know, don't drag it out. And for those people that run these longitudinal studies that last for years or decades, I don't know how to, I really don't know how to do that. There are some people that do that. It's absolutely amazing. They have like a team of people that constantly follow up all the time with their participants. Those are great studies, but personally, I couldn't do that. So maybe some of you will be better at keeping your participants than I am if you go into research. I'm not good at keeping my participants. Now let's move on to the factorial ANOVA. We're going to stick with two factors. So we're going to use two independent variables in these examples. Only because if we used more than two, it would be a complete nightmare. And even two independent variables is going to be an ask. It's going to be a reach. I feel that I'd like you to sort of understand it. I'm not sure if everyone's going to be able to do the computations perfectly. It's something that you got to practice, but I'm going to take that into consideration on the final exam. Is that yeah, it's more work. I'll keep the problems very basic, and if you do the homework, you're going to have probably harder problems on the homework than you'll have on the exam. Uh, but yeah, this is more computation than maybe some people like. And if I made it three variables, it would be impossible. Forget it. It would just be a nightmare. You would never want to do that. Two is enough. The independent variables can be manipulated by the experimenter, so you can randomly assign people to conditions, or they could be quasi-independent, which means that they're pre-existing groups, like gender. Gender is quasi-independent because you can't assign people to gender, right? You can't assign people to socioeconomic status. Those variables already exist. They're naturally occurring demographic variables, or race, ethnicity, or religion. These are all quasi-independent variables. So you can have either randomly assigned variables or quasi-independent or the preformed groups. Factorial designs consider more than one factor. We're going to look at two. I generally do not go more than three. And even three, if I had three independent variables, I would say that's hard. Uh, I've run a bunch of three-way ANOVAs, and it's confusing. It's confusing to make out the results. It's very confusing. With the two-way, you could draw nice line graphs that I'm going to show you here, and you can look at the line graphs and make sense of it. With the three-way, you would need to draw a three-dimensional graph, or you would need to have two two-dimensional graphs and look at them simultaneously. You can do it, it gets messy. Anything above three, I wouldn't do. So like if you had like four independent variables and you want to run them as a four-way ANOVA, that would be a disaster. that would just that would be like absolutely what you don't want to do because you would not be able to interpret it at all. You might find significant effects and you'd be like, oh wow, I got a significant four-way, and then you look at it, and you're like, how the hell do I look at this? You can't make sense of it. I don't even know how you would look. You can't look at a graph of a four-way interaction unless you can look in four-dimensional space, or you look at two three-dimensional graphs simultaneously. I don't see how it's possible. Last time I checked, you can't look at a four-dimensional graph. So let's stick with the two. There's going to be three F ratios when we do the factorial design here. You're going to have an F ratio for the first variable, factor A. You're going to have an F ratio for the second variable, factor B. And then you're going to have an interaction effect. an F ratio for an interaction effect. So each of these F ratios are done the same way that we did the other one. So it's going to be the treatment variance on the top, and the bottom is going to be basically the random chance. So if the null is true, this is the variation we'd expect by chance alone. That's going to be the denominator. So we don't have to worry about like separating individual differences here because we're not doing repeated measures. In this factorial design, we have different people in each group. So we don't have to worry about subtracting out, the individual difference variance. We're not doing that anymore. That's only for the repeated measures ANOVA. So here are some of the what are called the main effects. So the main effect is the effect of one variable, one independent variable, basically ignoring the other independent variable. So if you were just isolating the one variable and ignoring everything else, this is if that variable it causes a difference, basically. And so we're going to call the first variable A, and we're going to call the second independent variable B. And so let's say there's only two groups, right? So this is a 2x2 design. So you have two variables, and they each have two groups. So variable A has two conditions, and variable B has two conditions. So you have two variables, each one has two conditions, so you have a total of 4 conditions. So this is what's called a 2x2 factorial design. And 2x2 gives you 4. So you have 4 conditions, 4 groups, basically, and different people in each group. So the null hypothesis says that variable A, the mean of variable A is going to be the same in group 1 than the mean of variable A in group 2. So basically, across the two conditions for, let's say variable A is gender and you're looking at male, female. So this would say that the mean for males are the same as the mean for females. There's no difference. And the alternative would be that there is a difference between males and females. And let's say group B is whether you're introverted or extroverted, right? Or let's say introverted or not introverted. If you want to, because there may be some people are kind of like in the middle, they don't want to consider themselves introverted. So then the null hypothesis would say there's no difference between the introverts and the non-introverts. And the alternative would say there is a difference between the introverts and the non-introverts. It could be basically anything, but it has to be something with two groups here. I'm just giving you examples of things that have two groups, variables that have two groups. It could be any other variable with two groups, though. So the interaction term is when the impact of one variable depends on the presence of a second variable. So the effect of one independent variable depends on the levels or the conditions of a second independent variable. That's called the interaction effect. When one variable's effect depends on the levels of a second variable. Or the way the text talks about it, it says basically the patterns of mean differences in the groups are different than what you would expect by looking at the main effects. And you can see that better when I show you the table. But the null hypothesis for interaction term is that there's no interaction effect, and the alternative is that there is an interaction effect. Simple as that. So when the effect of one factor depends on the level of another factor, it's called an interaction effect. You can see the interaction effect in a graph. The easiest way to look at it is in a line graph. If the lines are parallel, there's no interaction effect. If the lines are not parallel, there is an interaction effect. And you can call this the A by B interaction because it's two variables. Or whatever the variables are, you can put the variable names in. Here's the best way to look at interaction graphs. Uh, these are much better than looking at the tables of the means. I think this is easier, but you can look at tables of means and find the interaction as well. If you look on the left, we have two variables. One is violent versus nonviolent. There's two, so this is level of violence. And there's two conditions, violent versus nonviolent, two levels, two groups. And then you have a second variable, male versus female, which is two more groups. So gender. So this is gender by violence. And as you can see here, on the left, there are parallel lines. So males and females, they increase at the same rate when you go from non-violent to violent. So I'm assuming they're watching something violent, or they're playing a violent video game, or one of these studies, right? You see the same difference in males and females. So the effects of violence on gender, there is no effect, right? They both increase. So we know that if you watch something, or you play some violent video game, or you watch violent TV, in this case, it's errors of some kind that you're making go up. They go up the same rate in both males and females. So the lines are parallel, there's no interaction. When the lines are not parallel, like in the graph on the right, graph B, that means there is an interaction. So in this case, the error rate stays the same. So violence has no effect on women at all. Females stay the same. But violence has a big effect on men. So men increase their error rate, whatever that error rate is, when exposed to the violent condition compared to the non-violent condition. So it seems like violence has an effect, negative effect on men, where it has no effect on women. That could be interesting, right? Um, you know, so why is that the case? Why are men are more prone, men are more sensitive to violence? You know, you could have men playing a violent video game, and maybe they get into more fights compared to women that play violent video game. Has no effect on them. Now, there's other things here. I mean, like, you know, you have things like age. That you have to, you know, consider here. So you'd want to gather people around the same age, you know, within a small age range. So you don't have like age as a factor that can influence this. Um, so there are some problems with drawing a conclusion from this, especially since we're using preformed groups, male versus female. That's not randomly assigned, obviously. So there's a flaw in the sort of conclusion that you can take from it. But overall, it seems like there is an interaction effect in B on the right, and that men are affected more by violence than women are. And that could be interesting if you know, control for age and all that other stuff. That could be influencing the result as well. So when we do this factorial ANOVA, we have to look for main effects. So the effect of the first variable, factor A, the main effect of the second variable, factor B, and then the interaction that I just showed you on the previous slide. We've got to look for all three tests. Separate F tests for each of these three. And the results are independent of the others. So you can have them all significant, you can have none of them significant, you can have the main effect significant, interaction effect not significant, you can have the interaction effect significant, the main effect not significant. So these three tests do not affect each other, they're all independent. Now computing it. The first stage, you have to compute the same way you did the regular ANOVA. Sum of squares total, sum of squares between treatments, and sum of squares within. That's the easy part. The second stage, a little bit more work. Not that much more work, but a little bit more work. This time, instead of, you know, in the repeated measures, we took the sum of squares within and we subtracted the individual differences. Obviously, we don't need to do that here because we're using different people in each condition. So we don't have to worry about individual differences. But we have to partition, in this case, the between groups variance. So we need to partition the sum of squares between treatments into the sum of squares that result from factor A, the sum of squares resulting from factor B, and the sum of squares resulting from the interaction. So these are three components that are driving the difference between the groups. You have factor A that causes the difference, first variable, factor B, the second variable, and then the interaction effect. So it looks like this. You have total variance. Within treatments, variance is going to be the same denominator for all three F ratios. You're going to use the same within groups variance denominator. But for the between groups variance, you need to find an F ratio for the first variable, the main effect of the first variable, factor A, an F ratio for the main effect of the second variable, factor B, and an F ratio for the interaction. So you're going to have three F ratios, and that's going to partition the between groups variance. So review from previously, sum of squares total is the sum of x squared minus the grand total squared divided by the total sample size. Sum of squares between treatments is the sum of the treatment sums in each condition squared divided by the number of participants in each condition. Once you've done all that, minus the grand total G squared divided by the total sample size, which is capital N. In this case, you're going to have 2 by 2. So if you have a 2 by 2 design, you're going to have 4 cells, 4 groups. So you're going to have 4 T's. You're going to have a T for each of the 4 groups. You're only going to ever have one G, because G is the grand total. But you're going to have a T for every condition. In this case, if we have 4 conditions, we're going to have 4 of these T squared over N terms to add up. And then the within group sum of squares, you're just going to find the sum of squares within each of the groups and then add those 4 sum of squares up together. Now, if I'm partitioning the main effects, I need to find a different formula for the main effect of A, the first variable, which is A, the main effect for the second variable, which is B, and the main effect for the interaction term, which is A times B. So the sum of squares for A is going to be the row total, right? So if you have 2 levels of one variable, right, you're going to have 2 rows. If you have 2 levels of the other variable, you're going to have 2 columns. So this row total is there's going to be 2 terms. So if you have 2 rows, you're going to have 2 of these T squared columns. So all you're doing is adding up the row. You're going to find the row sums. You're going to sum up each row and write that total in the right-hand column if you make a chart. 4 boxes, what the sum means. You're going to add up the numbers across each row, find the row sums, square each row sum. Here you're going to have if you have 2 levels of one variable, variable A, you're going to have 2 row sums. So square those row sums divided by the total number in the row. Total number of subjects comprising the entire row. So if you have 10 people in each condition, and you have basically 2 conditions by 2 conditions, you're going to have 20 people in each row, 10 and 10 in the 2 cells. And then subtract the grand total squared divided by the total sample size, capital N. And then the sum of squares for factor B, you're going to do the same thing with columns. You're going to use column sums, which is T squared column. So you're going to find those column sums, square them, divide them by the total number of people in each column. So add up all the cells in the column, and that gives you the total number of people in each column. And if you have a 2 by 2, you're going to have 2 rows, you're going to have 2 columns. So you're going to have 2 terms here for the columns. You're going to have 2 column sums. And then subtract the same term, the grand total squared over total sample size, capital N. Once you've done that, you can then find the interaction term by subtraction. So to find the interaction term, take the sum of squares between, which is what you're partitioning now, subtract the sum of squares due to factor A, which is the formula on the left, subtract the sum of squares due to factor B, which is the formula on the right. These are the main effects, sum of squares, right? Main effect for A, main effect for B. Subtract those from the between sum of squares between groups, between treatments, and that's going to, what's left over is going to be the interaction effect. Sum of squares A times B. So it's basically the residual, the leftover, when you take the total sum of squares between and subtract out the main effect for A and the main effect for B. That gives you the leftover, which is the interaction term. Sum of squares A times B. And the degrees of freedom is going to be very similar. Degrees of freedom total is n minus 1, so that's the total number of people across all conditions, minus 1. Degrees of freedom within is the sum of degrees of freedom inside each treatment, which is going to end up being n minus k, where k is the number of groups. The sum of squares between is going to be k minus 1, where k is the number of cells, right? So in this case, with the factorial design, remember I said k is the number of groups? Groups are the same thing as cells. So groups are not variables. Groups are total cells. How do you know how many cells you have? Well, you multiply out. If I have 2 conditions or 2 levels of factor A and 2 levels of factor B, multiply them out and I get 4 total cells, 4 total groups. If I have 3 levels of factor A and 2 levels of factor B, 3 times 2 is 6. So now I have 6 groups or 6 cells. If I have 4 levels of factor A and 3 levels of factor B, 4 times 3 gives you 12 groups. So that's how you find the number of groups you have. So k is the number of groups. The degrees of freedom A is the number of rows minus 1. The degrees of freedom B is the number of columns minus 1. And the degrees of freedom of the interaction A times B is just the degrees of freedom between minus degrees of freedom A minus degrees of freedom B. So if I have 2 rows and 2 columns, then I have 1 degree of freedom A, and I have 1 degree of freedom B, and 2 by 2 gives me 4 total conditions. So I have 3 degrees of freedom between. So if I have 3 degrees of freedom between and 1 for A and 1 for B, that leaves 1 left over, and that 1 is for the interaction term, A times B. Simple as that. Just subtract. And it seems harder listed like this instead of, sort of illustrated. But that's why you have the tutorials, and that's why you have the homework, and that's why you have the sample problems on MindTap, so that you can go step by step at your own pace, rather than me just do the problem. And when I do the problem, it'll seem very easy. This is what always happens. I do the problem. I can put the problem up on a computer. It's going to seem very easy. And you're going to look at it and you're going to say, okay, I know how to do it. I've seen him do it. It's good. I get it. And then you're not going to know anything because you're looking at me doing it and you're not doing it yourself. This is the same problem I have in a face-to-face class, which is why I'm telling you now, watch the tutorial problems, do the step-by-step on MindTap, they have the demonstration problems at the bottom, not in the assignment, bottom, you have the demonstration problems. Do that. It goes through step by step. And so it'll test you to show the work. And then you could do another problem and another problem. And all the problems are different. So you're actually doing them on your own time, on your own terms, and you're finding where you're making a mistake. Versus me just doing the problem and you watching it once or twice and saying it's easy. I can certainly do that. I mean, you can email me, set up an appointment, whatever, and I can work out the problem. I just don't find that to be the best thing. The best thing is for you to do the problem, practice it, fix your mistakes, learn from your mistakes, and that's why the interactive software is important, because it's actually allowing you to practice the problem on your own terms and giving you feedback when you made a mistake, versus me just doing the problem and it being easy, and then you look at it and say, okay, I get it, and then when the test comes, you're like, well, it seemed easier when I looked at it. When he did the problem, it seemed easier. That's always the response I get from students. oh, well, you did the problem in class and it was easy. I understand everything that you're doing in class. Well, yeah, obviously. It should be easy to me. If it's not easy to me, then there's something wrong, right? Then I should be teaching the class. But just because it's easy to me and it seems like, you understand it by watching me do it, doesn't mean that you know how to do it. So that's what I'm saying. Do the tutorials, sit down, take out a piece of paper, go into the book, find some problems, sample problem, or find a problem in the back of the chapter, and do it. And see if you can do it from scratch once you've done the walkthroughs online. And that'll really tell you if you know what you're doing. And then if you hit a snag, reach out to me. If you can't figure it out, I'm here. I answer questions all the time. I answer questions through email. I answer questions through Zoom. Obviously, it'd be better if I can answer the question face to face, but due to the current circumstances, we can't do that. But definitely through either Zoom or through email, I can do it. So, just let me know. There's more formulas for you. So these are the same formulas as you had before. There's a lot of formulas here. They're all variations of the same thing. The mean squared is the sum squared over the degrees of freedom. The only thing that changes is whether it's for factor A, factor B, or the interaction term. So it's the same formula, just you change the term. And then the mean squares is going to be the sum of squares divided by the degrees of freedom. That's the error term. So that's the denominator of the F ratio. So you should have done that at the beginning. When you do the between, you do the within, you save the within, and the within becomes the denominator of all these fractions. So the only thing I'm changing is the top, the numerator. For the main effect of A, I want the mean squared of A. For the main effect of B, I put the mean squared of B. For the interaction effect, F, I put the mean squared of the interaction. The denominator is always the same. It's always MS within. So 3 different numerators, same denominator. And then when you compute it all, you can make a nice, lovely graph like this, table, I should say, where you have the sum of squares, degrees of freedom, mean squares, and F. You have your total between groups, between treatments, sum of squares is 200. And look how they all add up. So the 200 is broken down as 40 for variable A. The main effect for A is 40. The main effect for B is 60. And the main effect and the interaction effect is 100. 100 plus 60 plus 40 gives you 200. So it's just partitioned. The between group sum of squares has to be equal to the main effect and the interaction when you add them all together. And it is. The degrees of freedom, you need to break out the degrees of freedom. So if you have 3 degrees of freedom between, that has to be broken down to those 3 terms, the main effect, and the interaction effect. 1 plus 1 plus 1 gives you 3. And then to find the mean squared, you take the sum of squares divided by the degrees of freedom. This gives me 4, this gives me 6, and this gives me 10. 6 and 10 being significant, 4 not being significant. With the degrees of freedom between here is going to be 3, and the degrees of freedom within is going to be 20. So you'd find the critical value, you'd find 3, 20. So you always want between and within as your degrees of freedom. So 3, 20 in the table. So 3 on the top of the table, 20 on the side of the table. Find the critical value and see if the F is above the critical value. In the case of 6, it is. So there's a main effect for B here, and there's an interaction effect because that F ratio is 10. And the critical values are listed. You see the critical value for the main effect is 1, 20, and the critical value for all of them is 1, 20 for the 0.05 critical value. Overall, though, you could see, you could test overall if the ANOVA is significant, although that doesn't really matter, but you can test overall. If you did 3, 20, you can see overall if there's significance. But if you just want to test the main effects and interaction, you have to look at the individual degrees of freedom for the main effects in the interaction. In this case, they're all 1, so it's going to be 1 comma 20. To find the effect size, we need to compute the partial eta squared. So the main effect of A is going to be the sum of squares of A over the sum of squares of A plus the sum of squares within. For the main effect of B, it's going to be the sum of squares of B over the sum of square of B plus the sum of squares within. And for the interaction term, the effect size is going to be the sum of squares of the interaction term over the sum of squares of the interaction term plus the sum of squares within. So nothing groundbreaking here. This is partial eta squared because we're not using the total variability, right? We're using a partial variability in the denominator. So that's why it's partial eta squared. Now that really doesn't really make much of a difference. Eta squared, it's effect size, basically, for the ANOVA. If you're reporting this in APA style, you want to put the F, you want to put parentheses, the degrees of freedom for each term, for whether it's the main effect or the interaction. And then you want to put comma the within group's degrees of freedom, which is 20 here, equals the actual F value you obtained, 6.33. We know if it's less than 0.05, you can write P as less than 0.05. So if you reject the null, you're going to write P as less than 0.05. And then you're going to list the partial eta squared, the effect size, which is moderate. Moderate to large, 0.478. You could also, I would say for ANOVA, if you have an interaction term, you want to use, you want to give a graph, a line graph, because that's easy for the reader to follow. The line graph is very helpful. So you can also include that. That matters for interpreting the results. The line graph helps you interpret the interaction. So if you want to show a line graph, or if you want to show a bar graph, I like the line graph better, but some people like bar graph. That allows me to look and visualize the interaction rather than just listing the means. It helps the reader interpret the results. And it's going to help you, the writer, the author, interpret your own results. So I always make a graph when I have an interaction. I graph the interaction and I try to make sense of it. Sometimes you have interactions that don't make sense. And if the interaction does not make sense, I'm not sure you really want to report it. If you can't interpret it, then someone else is going to interpret it. I mean, or sometimes the interaction is opposite of what you think is going to happen. In that case, do you have a story to explain it? Can you explain it and why it came out different than you thought originally, than you hypothesized? Just because you have a significant interaction doesn't always mean it comes out the way you want it to come out. I've had plenty of interactions that come out the opposite of what I thought. And sometimes I can make sense of it, and sometimes I can't. If you can't make sense of it, I just wouldn't report it. Because if you can't make sense of it and you report it, people are going to expect you to be able to tell a story based on your interaction effect. If you can't tell a story, you're not going to get published. Here's a significant interaction because the lines are not parallel. The lines are not parallel, and you can see that quiz score depends on whether the questions are given on paper or a computer screen, and whether you have fixed time or you have basically as much time as you want. And it looks like for fixed time, it's a good thing to be presented on a computer screen. It's a little bit, the results get higher, get better. So if you have like a time test and you take the test on a computer, you seem to do better than if you took the same time test on paper here. That's that red line that's going up. Now, is that significant from paper to computer screen? Basically, another way of saying that is the slope of that line significantly different? Significantly different from zero. And the answer is, I don't know based on this. I'd have to do what's called simple effects on this. And I have to do like a t-test basically to see if the means are different from paper to computer screen for the red line, because it's very close. It could be significant, it could be not significant. So maybe if it's not significant, there's no difference with fixed time. But for self-regulated time, which is basically you're given as much time as you want, performance is worse on a computer screen. And maybe that's because eye fatigue. You're staring at the computer screen for so long, and so long, and so long. Or maybe you feel like you can stare at the computer screen for a much longer time than you can like stare at your test if you're in class taking a test. And you just feel like you have to hand in the test eventually. You can't just stay there forever. Even if you were given unlimited time, would you sit in your class for like 10 hours and take the test? Probably not. You look around and you see everybody leaving, and you'd be like, okay, it's been 2 or 3 hours. I just give up, right? But if you're doing it in front of a computer, maybe you don't have that same kind of feeling. And the more time you spend on it, eventually you sort of, screw up. I don't know, you get tired looking at the computer. There's a lot of different reasons for this. But it seems like having self-regulated time, given like personal, different times for different people, may not be the way to go. And that's kind of how I feel. It's like you need to have enough time, but you don't want to give unlimited time. I remember I had unlimited time and I took an exam when I was a student. I took an organic chemistry exam. It was an organic chemistry final, organic chem 1. And I took it for 7 hours, the exam. It was right before Christmas. And it was kind of crazy. I was in class too, and I took it for 7 hours. No, I did really well on it. The exam was 17 pages long. So it kind of did require like a long time. But I remember taking the test starting at like 1 o'clock, and I left and it was like 8 or 9 o'clock. It was some crazy thing like this. And my professor she was just nuts to give us like a 17-page test. I guess she figured most people would just like, after an hour or two, like people were leaving after like 15 minutes. They were scoring like, 6 on the exam. I don't know what her goal was to like make people absolutely miserable. I don't know. But I took all 17 pages. I finished all 17 pages, including all the reactions. No, I mean, not the reactions. The reactions won't test. All the synthesis problems at the end, where you have to like start with a particular compound, then you have to do all the reactions to end with it, and there's like 10 steps. So for those I've taken Orgo, you know what I'm talking about. The synthesis problems are brutal, and it was fun. Strangely enough, those were the good old days. I sit there for 8 hours and be like, okay, this is fun, right? But yeah, I think that there should be like a time limit for certain things, because I think some people like myself get carried away when you're given unlimited time. Some of the assumptions of the two-factor ANOVA, the same as the univariate or one-way ANOVA. Independence of observations. Samples must be normally distributed. Samples come from populations that are normally distributed. Chances are they'll be normally distributed if they come from populations that are normally distributed. And homogeneity of variance. So the largest variance should be no more than 4 times the smallest variance. It's kind of the rule of thumb. But you could test it formally with Hartley's test or Levine's test again. Learning check. Two-factor analysis of variance produces a significant interaction. So when you have a significant interaction, you need to, generally, if you have a significant interaction, you should ignore the main effects. Remember that the main effects and the interaction, they're independent of each other. But if you get a significant interaction, then you really don't want to put too much stock in the main effects. You want to focus on the interaction. So in this case, it doesn't matter what happens with the main effects. They don't affect the interaction. So there's no effect. They're all independent of each other. And that's answer D. The significance of the main effects is not related to the significance of the interaction. They're not. But if you get a significant interaction and you have significant main effects, you want to prioritize the interaction. You don't want to put too much stock in the main effects because the interaction trumps the main effects when it's significant. True, false. First statement says two separate single-factor ANOVAs provide the same information as obtained from a two-factor ANOVA. Obviously not. Because if you do a single-factor ANOVA, you can only find a main effect. You can't find the interaction effect when you're doing a single-factor ANOVA, obviously. And the second one, a disadvantage of combining two factors in an experiment is you cannot determine how either factor would affect participant scores if it was examined by an experiment by itself. While if you're combining two factors in an experiment, you can find the interaction effect, but those main effects don't make much sense once again. So the first one was obviously false because you can't find an interaction effect. The second one is also obviously false because the two-factor ANOVA allows you to determine the effect of one variable controlling for the effect of the other one. But once again, the interaction effect trumps all the main effects. And here is a breakdown, the math breakdown of what you have to do with the two-factor ANOVA. So you start with the total sum of squares, the total degrees of freedom. You're breaking it down into between groups and within groups. Within groups, you're going to stop because once you get to within groups, you calculate that, you're done. For within, you've got the denominator. For the between, you got to partition into three different ways. You have factor A, you have the main effect for A, you have the main effect for B, and you have the interaction, which is found by subtraction. And then you take those sum of squares, divide by their respective degrees of freedom, and you're going to get the mean squared for main effect of A, you get the mean squared for main effect for B, and you get the interaction term, and you're going to compute their F ratios. And then you're going to look up to see if they're significant. And then you're done. And that's a long problem. But it's kept relatively simple in the chapter in that they use very basic designs. It can be a really enormous problem if you have a lot of participants and you have a lot of different factors or many levels. It could be really burdensome. I've done these things. Some problems were so big with like 3 or more interaction terms that it would take me an hour to do one problem. You're not going to have that situation because I'm keeping it very, very basic. So I'm giving you basically all the information. You just need to find some 1 or 2 calculations. I'm not going to have you compute huge problems because it's just not worth it. I mean, you can do that in your spare time if you want to like torture yourself, or if you enjoy doing math. I mean, some people enjoy doing math. So, but we have really powerful computers that will do this problem for you in like, less than a second. And Excel is not one of them, unfortunately, but you have SPSS, which we really didn't get to learn this semester because of the lack of being in school. And you have SAS, you have Systat, you have R. And R is free. And R is something that R and Python are 2 things that are really trending as far as data analysis goes. And those are things, if you're interested, reach out to me. Reach out to me about anything. And if you're interested in learning about more, I'm happy to direct you, give you stuff to really, look at. I give you stuff for SPSS, R, Python, not so much Python because I don't use that too much, but SPSS and R I use all the time. And R is free. So if you want to learn more about it, let me know. I'll be happy to. Or you just want to learn about other things, happy to talk about it. This is one of my favorite topics. So it's not so many people that really love this, but I'm one of these people that really loves this stuff. So feel free to reach out to me. So hopefully this helps a bit. I know it's a lot of information. You're going to have to practice. And if you have a problem, let me know. And, you just got to have to practice. It's one of these things. I know it's a difficult time of the year, difficult time with all that's going on and stuff. But try to set aside a little bit of time to practice this stuff. And if you have questions, let me know. So bye for now. Hope that helps. See you next time.